I'd like to continue talking a little bit about partial derivatives, but we're going to do a slightly more complicated example in order to get at some of the things that are issues that one deals with in thinking about partial derivatives, and also a little bit about interpretation. So the example that I want to use is an example that you messed with in the last studio, right? It's this example of how the temperature in the ground varies both as a function of what the time of year is and as a function of the depth, right? And so you recall that example from the reading where, if I sort of were to plot, so let's say this is depth, this is time along the x-axis, or along that axis. This is terrible. Time goes in that direction, depth is in that direction, and temperature is in that direction. You'll remember that in the reading, the sort of idea is that the temperature at the surface varies sinusoidally during the year. As you go deeper, the temperature variation gets smaller, so this amplitude is decreasing, and also there's some phase shift that happens as you go deeper because of the delay associated with the heat getting deeper into the ground. So I encourage you to look back at the reading for a prettier picture of this. And I'm going to just propose a function that does something like what we want it to do. So I'm going to propose a function that says my temperature is an amplitude that depends on depth, right, times a sinusoid, so they say times the sine of omega times t minus some constant times depth, right? And so what this is going to do is the amplitude is going to get smaller as d increases, and obviously the sinusoid is just a sinusoid, but it has a phase that depends on how deep I am, okay? And I'll go a little bit further and actually say what I want the amplitude to be. The amplitude is simply going to be some maximum amplitude times e to the minus d divided by d naught. So I'm assuming that this amplitude drops off exponentially as I go into the Earth. So now we can write out the function completely, sine omega t minus c times d. And I'm not claiming this is the solution or anything. It's just a reasonable function, and it'll be interesting to think about. Okay, so let's think about partial derivatives of this function. And if we look at the function, we've actually defined this as being a function of two variables, right? It depends on time, and it also depends on depth. Now, you could also say actually it's a function of more than two variables, because clearly it depends on these other parameters as well. I'm going to call those parameters right now rather than variables. So I'm thinking this is a function of two variables as illustrated by the diagram. So we might ask two questions. One is, if I take the partial of the temperature with respect to time, what does that tell me? So what does this mean? And then also, what is it from a sort of calculational perspective? What's the expression? So let's start by actually finding the expression, and then let's think about what it means, and then we'll do the same thing for the partial of the temperature with respect to depth. So the partial of the temperature with respect to time, if I want to find the expression, I'm going to take partial with respect to time of a naught e to the minus d over d naught sine of omega t minus c times d. Okay. And to take this partial derivative, I'm going to hold d as a constant and assume that I'm just looking at a function that depends on time, right? So here I've got a constant times sine of omega times t minus another constant. And if I go ahead and simply evaluate that, hopefully not doing anything stupid since this is on video and everyone in the world can see Mark making stupid calculus mistakes, I think I'm going to get a times e to the minus d over d naught, right? Because this is a constant, it's just going to come down. I'm going to get a cosine of omega times t minus c times d, right? And then chain rule on the sine will pick up a factor of omega out front, and the derivative of sine is indeed positive cosine, right? Yes, I don't think I did anything stupid there. So this is what the partial of t with respect to time is. It's omega times all this crap. Okay, that's an example of doing the calculation. What's it actually mean? Well, what this tells us is how fast is the temperature changing with respect to time in a given location at a given time, right? And so we can actually evaluate this partial derivative at all kinds of different locations and times. So one of the things we could do is ask the question, well, how fast is the temperature changing with respect to time if I'm really deep in the ground? If I'm really deep in the ground, this leading term is going to be very close to 0, right? Because this exponential is going to drop off. So effectively, if I'm deep in the ground, the partial of the temperature with respect to time is close to 0. In other words, deep in the ground, T is not changing very fast with respect to time. I can also see that it actually is going to change differently with respect to time at different times of the year. So for example, this cosine of omega, if I ask the question, how's it changing at the surface at different times of the year? Well, there are times of the year when it's not changing very fast at all, where in fact it's not changing at all when the cosine is 0. And there are also times of the year when it's changing pretty quickly when the cosine is 1. So depending on what season it is, the temperature changes faster or slower as well. But this function, which is the partial of the temperature with respect to time, gives me all this information about how fast the temperature is changing at a given location and at a given time. Now we could do the same thing with respect to depth. If we think about what that means first, that means how fast would the temperature change if you were to change your location while keeping the time the same. So in other words, if you're sort of asking the question, what's the rate of change of temperature with respect to depth at a given time of the year, okay? And to evaluate that, we'll take the partial with respect to depth of a naught times e to the minus d over d naught sine and blah, blah, blah. Okay, and now we need to be a little bit more careful. We're going to have to use product rule to do this. We're going to treat t as a constant because we're taking the partial with respect to depth. So when we product rule it, we're going to have to take the derivative of this times that, and then the derivative of that times this. So our first term is going to give us a naught e to the minus d over d naught times negative 1 over d naught, right? Times sine of omega t minus cd. And our second term from product rule will give us a naught times e to the minus d over d naught times cosine of omega t minus c times d times negative c using product rule. Okay, so there's what our partial of the temperature with respect to depth is. And it's kind of ugly, but it tells us this information about how strongly the temperature depends on depth. In other words, sort of what's the sensitivity of temperature to depth at a given depth and at a given time of the year.